In the previous videos in this series, I showed you how to use the command terminal or executable version of CrystalGrower on your local machine. But the true benefit of using CrystalGrower as an executable is that you can run it on a supercomputer or high-performance computing systems. There are two examples of these architectures at the University of Manchester that you can easily get access to. The first one being Condor, which I have shown on my screen here, and the second being the Computational Shared Facility, which we're also allowed access to. The Computational Shared Facility has more resources at the University of Manchester, but research groups are encouraged to contribute to the costs of this system. I'm going to go through using Condor, as this is the one I've always used. The architectures are similar, but some of the commands differ slightly in their syntax, and also the format of your submission file is slightly different. But both systems have a lot of documentation explaining how to use them. The first thing you need to do is actually request an account, which is what this page is showing here. I'll put a link to both the account request pages for Condor and the CSF in the video description. Along with the account request page, there's a lot of instruction documents down the side here, which tells you how to use Condor and a few guides on good Condor behavior. For example, this do's and don'ts page tells you things that you should do and shouldn't do, to avoid getting in trouble with other users of Condor. The main point is to consider the group of jobs you're submitting before you submit them. Check your input files several times just to make sure they're all correct, so you don't waste university resources. But how do we actually access Condor? If you're off campus, you'll have to log on to the Global Protect VPN and ensure it's enabled and logged in on your computer. Once connected, you'll need to log on using a secure shell program. If you're on Windows, you'll need to use some software, for example Putty, which is what I use. There are other alternatives. Provided you have a user account, you'll know what the host name or IP address is for Condor. So I've already saved it. So in this case, it's my username at submitter.itservices.manchester.ac.uk. If you're using an Ubuntu or Mac machine, you can actually log on to this straight through your terminal. You would just type SSH space, then this address here. And if we press open, it will open a terminal and it will ask for my password. So this will be my university password. Note that you won't be able to see what you're typing on the keyboard when you're entering the password on here. And then you'll enter into your home directory. If I type ls on here, I've got two folders here, Intel and Scratch. So Scratch is where all your simulations will be run. So if we go into Scratch, cd Scratch, ls, this is where I saved all my simulations. So a quick note I'll make about preference for commands. I'll just note here that this terminal environment is the same as what you'd encounter on a Mac or Ubuntu machine. So it's useful to be familiar with the commands that you'd use on those systems. If you're familiar with the terminal, you'll also be aware of how to use aliases for commands. If you've got a command that you use over and over again, but it's quite a long command to type in, you can use aliases to shorten this down to a smaller phrase. And you can do this the same way on Condor as you can on Ubuntu or Mac machines, by editing your .bashrc file. So if I type Emacs, which is another text editor similar to Nano, Nano is also available on Condor, but I just prefer Emacs, .bashrc, it'll open this file here that I've already edited. So I'll highlight these lines down the bottom, which are my alias commands. So I've changed a few of the Condor commands to some shorter phrases which I'd used previously on a different HPC architecture, but you can change any command that you want. So if we want to quit using Emacs, you can press Ctrl-X, Ctrl-C, and that will quit. If you've edited the file, it'll give you options to save or overwrite. But on Condor, it doesn't automatically read from your .bashrc file unless you tell it to. So to do that, you have to type the command source. So source.bashrc, provided you're in your Scratch folder, this will work, and press enter. And then you'll see that my command prompt has changed slightly. So if I now type ll and press enter, you'll see that it's executing the ls-l command. So we've talked about getting access to Condor and setting up our terminal with our aliases, but what if you want to transfer files from your computer up to Condor? There is a way to do it using Putty, but it's a really long and cumbersome command, so the easiest thing to do is to get some software to do it for you. So I use a program called FileZilla. There are a lot of other programs, another example being Fetch. And these bits of software are designed to transfer files between your system and another system that you've connected to remotely. So if I open FileZilla, you can see on the left I've got my local site, but I need to connect to a remote site. So in this case, I need to open Site Manager and I need to connect to Condor. So you can use these settings here. You'll see the host is the same as what I use to log on to PuTTY. My username is the username for the university, and my password is my university password. So you don't even have to type this to log on like you do for PuTTY. And you have to make sure you have SFTP set up here as your protocol. Once you've set this up, you don't have to do it all again. It's saved in FileZilla. So if I select Condor and I press connect, it will then give me some progress updates in the corner here, and then you can see it's logged on to Condor on the right here. And I can go into my Scratch folder, and I'll be in the same folder now as I am on PuTTY. So you'll use software like this to transfer files up to Condor, and also download your completed simulations to your machine. So let's try an example of uploading. Now let's say, for example, I want to upload a new version of the CrystalGrower source code and compile it on Condor. The first thing I'll do is I'll go into my CrystalGrower code file here, and I'll create a new folder or directory, and I'll call this tutorial. And if I go into that folder, I'm now in an empty directory. Now I'll need to find the file that I want to upload, which is my Fortran source file from my computer. So this .f90 file here, and I'll drag that over to Condor. And it'll notify you when the transfer's finished. So now I can go back to PuTTY and go to that folder. So if I go into CD CrystalGrower code and then CD tutorial and type ls, you can see I've got my Fortran source file up on Condor. But now I need to compile this into an executable on Condor. The command that you'd use is ifort, but if I type this and press enter, you'll see that the command is not found. That's because when you're on Condor, you have to load modules to allow access to certain programs. So if I type module, if I double tap tab, it'll give me some possible commands. So if I type module list, it'll say I've got no module files currently loaded because I haven't loaded any. If I type module avail, it'll list all the possible modules that I can load. So the ones that we want are the Intel compilers for Fortran. So if I type module load Intel, it'll autocomplete if I press tab. If I press 15 and then press enter, it'll load the Intel compilers. So if I now type module list, you'll see that I've got the Intel compilers loaded. So now we can try compiling the program again. So if I type ifort, press enter, it'll now recognize the command, but I'll have to actually format it correctly. So ifort CrystalGrower, and then I want to give the executable a name. So the -o flag is required, and I'll call this CrystalGrower.x and press enter. Then it'll take a bit of time to actually compile the program. But if I now type ls, you can see that it's now compiled the program. All the module files are listed and the CrystalGrower.x file is available. So now I have the tools available to set up a simulation. So if I go to one of my folders that I've set up previously, I go to my tile simulations, and I'll go to the tutorial folder. So in here I've set up a folder to run some calculations on the chabazite structure, which is a tile-based structure. If you're running a net-based structure, it's a little bit more complicated because you need to consider where the net.txt file goes. But once I've set up the folder, hopefully it'll be more obvious what you're supposed to do. So I'm going to clear the terminal just to make it a bit tidier. Type ls again. So I've got quite a few files here which are all essential for running a series of simulations on the chabazite structure. So chabazite has 2 tiles in the structure, and I want to look at all the combinations of the energies of those tiles between 2 extremes. So you could just run hundreds of simulations manually on your machine, where you change one number at a time, but that's very slow and there's much easier ways to do it by using some scripting in Bash. And I'll also note that it takes about the same amount of time to set up one calculation on Condor as it does to set up 100 calculations on Condor. So you may as well use Condor when you want to run a batch of simulations. So there's a few files you'll be familiar with from the previous videos in this series, which will be your input.txt. So if I emacs input.txt, you'll see that I've set up a single calculation for Chabazite here. And my simulation name is 0_CHA. That's important because this is the line that's going to be changed by my script whenever we create a new simulation. Otherwise, they're just going to continually overwrite each other. Then we've also got CHA_new, which is our structure file. We have CrystalGrower.x, which is our executable that we just generated. We have CHA facets found rhombohedral.txt. That's our facets found file that I've already generated for Chabazite. Then we have our add input.txt. So if we look at our add input.txt, you'll see that I've got these two strings here, variable 1 and variable 2. So these are the variables that I want to change over my set of simulations. So I said earlier that I want to look at all the combinations of energies for these two tiles. This is the point where you would assign the two energies in your add input.txt. So by setting these as variable 1 and variable 2, I've got a regular expression or a phrase that I can search for to replace using a command such as sed, which I showed in the video previously. In this example I use Perl, but they both work the same way. So what I want to do is set up a loop of some kind which will generate a folder for each simulation. I want it to copy all the essential files in that it needs, which are input.txt and addinput.txt. I then want it to go through those files, increment the name of the simulation because we don't want it to keep overwriting itself, and then we want it to increment the variables in these add input files here. And we want that to happen for every simulation. So the easiest way to do that is by writing a bash script, which I already have prepared here. So if I emacs my combinations test2 script, you can see that it's an executable because it's colored in green. You'll see I've written a small bash script here. So your script doesn't have to look like this one, but this is quite a simple script to follow. You can easily make it more complicated or less complicated depending on your needs. But you can copy the lines from this script and edit them however you want. So I'll just explain briefly what it's actually doing. So at the top of the file you have to have this line here to notify the system that it is a bash script. I then have a variable called counter, which I'm setting to 0, because my simulation numbering is going to start at 0, Condor requires that. And then I've got my two variables, energy1 and energy2, which I'm starting at 2.0 kcal per mole. So these are the variables that are going to increment with each changing simulation. Then we get to our first loop. So this is a for loop in bash, which means it'll execute based on a certain condition, if a certain condition is satisfied. So here I've just said for I in sequence 0 to 4. So this loop is going to execute 5 times. So it's going to execute 0, 1, 2, 3, 4, which is 5 times. And all the following code is within that loop. So I'll say do, and it will echo energy1, which is just a string, and then it's going to echo the value of energy1 at this point in the loop. Then each time this loop executes, it's going to set energy2 as 2.0 kcal per mole, because we want it to be reset to the starting value of energy2 when we're running the next loop. Otherwise, energy2 will just keep getting larger and larger, which in that case we're not testing all the combinations between two numbers. Then we get to our inner loop, which is this line here. So it's another for loop. It's also executing 5 times, but our loop counter in this case is our variable j. And the first two lines do the same thing for energy2 as it did for energy1. It prints the string energy2, and then prints the value of the energy2 variable. This is just so the user can tell which simulations are being set up, it just prints them on the screen. Now we know that we want a new folder for each simulation. So this is the loop that's going to be executed for every simulation. This is the point where we need to make our folder. So we have this command here, make directory, and the folder is going to be called whatever the value of the counter variable is. So it starts at 0 and then is incremented at the end of this loop. We then copy our input and add input files into these folders that we've generated. You can also copy your facets found file. But if you're using the same one for a batch of simulations, then it's not necessary. You can store it in the folder above without copying it into every subfolder. Then we move to our string editing commands. So in this case I'm using Perl, but you can use sed instead if you want. So what this first line is going to do is go into the input.txt and it's going to search for that 0 underscore, which is the name assigned to the simulation, and it's going to replace it with the value of counter. All this is going to do is make sure the name of the simulation matches the counter number that's assigned to the folder. So no files are going to be overwritten, and each simulation's got a unique identifier. Then we start editing the variables in addInput.txt. So this first line is going to search for the phrase variable1, and it's going to assign it the value of the variable energy1. And then this next line is going to do the same for variable2, but assign it the value of energy2. The following line here is commented out. This is what you'd use on a local machine to actually run the code feeding in the addInput.txt. But we don't want that on Condor because we're going to submit them to the queue. So we don't want to actually execute the program in the folder, we just want to set up all the folders. Then our counter variable is going to increment by 1, so that's what this counter ++ means, and it's in 2 sets of brackets, which is required by bash. Then we get to one of the more important lines here. So this is a line where we increment the energy2 variable by a certain amount. So we're actually incrementing energy2 by 0.1 kcal per mole, as you can see here in the line. But bash doesn't have an easy way of incrementing variables by floating point values. So you have to use this fairly complicated command where you use the bash calculator, which is what BC stands for, and then print that variable by using echo. But the effect of this is that energy2 will be incremented by 0.1 kcal per mole. If you want to change the spacing, then you'll have to change this number here. Or you can add an additional variable at the top of the file and call it spacing2, for example, and you can change that value at the top. Then we finish our inner loop. So all the code between that second do and done will be executed 5 times for every time the outer loop is executed. So 5 times 5, 25 simulations. Then we finally increment our first variable, energy1, by the same amount, so we use the same command as we used for energy2. I'll also note that this scale equals 2 defines how many decimal places you want to go to. So in this case, 2 decimal places. And then we type done, which completes the outer loop. So energy1 will be incremented 5 times, and energy2 will be incremented 5 times per increment of energy1. So the total number of combinations is 25, so we'll have 25 simulations numbered from 0 to 24. And running this script will set up all the files correctly in all the right folders to be executed on Condor. So let's go back to our directory and look at the files that we're going to start from, the addInput and input files. There's a few peculiarities you need to be aware of when you're using Condor related to file paths in your input.txt. So our input.txt files and addInput.txt files for each simulation are going to be in subfolders. On the top level there's going to be one CrystalGrower executable, one structure file, and one facet coloring file. That's going to be used by all the simulations. So you'd think that if they were in the directory above, the file path for the structure file would be // new and // cha facets found rhombohedral. But with Condor you have to actually write that they're in the same directory, because these files will be copied and pasted into the same folders to run. So these need to be defined relative to the executable file, not relative to the input.txt. It is a bit confusing, but it's something that you need to make sure you get right, otherwise the simulation won't run correctly. Once you have your template file set up correctly, which is what I'll call this top level input.txt, we've got a simulation named 0cha, and we've got the parameters set the way we want them to be. We now need to look at our addInput template file. So if we emacs addInput.txt, we can see that's also set up correctly with the answers in the correct order. So this first question will be related to the queue scaling. Do you want it to be the same? Then the next question is related to the tile scaling. Do you want them to be the same? So in this case we don't, so we answer no. Then we input the energy variables for each tile, which is going to be incremented by our script. Then we ask for the baseline scaling. Then the memory parameters. Because we're running on a computing cluster and we're going to be requesting a certain amount of memory, I've chosen to define my memory box manually. You can allow CrystalGrower to do this automatically on a cluster. This might lead to your memory requirements changing per simulation. So you're at some risk of your simulations not being run, depending on the memory that you're requesting. But there's also a risk when you define your own box that your crystal will reach the edge of the box and crash the simulation anyway. So it's up to you which one you use, really. Then these two values here are related to our delta mu mode. We're using mode 3. So the first question is how long it will take to equilibrate in iterations. And then the second figure is related to how long it's going to stay at high supersaturation for. So this will stay for half the simulation. So 5 million iterations out of 10 million iterations. And then we're also going to color all the simulation outputs using the same facets found file. So now that we know that all of our template files are set up correctly, everything's in the right place, we can run our script to set up our folders. So if I type // then the name of my script, which is combinationstest2.txt, press enter, you'll see the echo commands print out all the energies that are being assigned. And if I now type ls, you can see that we've got 25 folders set up. If I go into folder 0 and look at addinput.txt, you see that my energies are starting at 2 and 2 kcal per mole, which is what I set for them to start as in our script. And if I look at the input.txt, you'll see the simulation is called 0_CHA. Now if we jump to the final folder, which is CD24, if I look in add input here, it's reached 2.4 kcal per mole for each of those tiles. And if I look in input.txt, the simulation's called 24_CHA. So all of our files and folders are set up correctly now. But there's one more file we need to set up to submit all these simulations to the queue, and that's this Submit Txt file that I've got saved. It doesn't have to be called that, it can be any name, but it needs to be located in the same directory as your executable and your folders that you're going to submit as simulations. So let's have a look at the format of that file. So most of this is just copied straight off the Condor website. It just lists a set of criteria for the types of machines that you want to run on. You can pretty much copy this file exactly as is, but there's a few lines you need to be aware of editing for your own jobs. So the main one here will be request memory. So here I'm requesting 3 GB of memory, because I'm only running some small simulations for Chabazite. If you're running more complicated structures or longer simulations, then you will have to increase this number. I tend to increase it 1 GB at a time, but the more you request, the smaller your resource pool is of computers that you can submit to, because you'll be relying on more high power machines. You can also request a certain number of CPUs, so processors. In this case I've requested 2. CrystalGrower generally only needs 1. It's not very processor intensive, but it is very memory intensive, which is why we're ranked by memory up here. But sometimes by requesting more CPUs you can get your jobs to run on 1 computer, so it's unlikely that it'll be evicted or restarted. Then we set up a series of output files for the simulation. So the log file here will write out what's happened to your job as it's run through the pipeline. The output file here will write out all the terminal outputs that's written by your program. And the error file here will write out if any error occurs and stops your simulation from running. A notification equals error will notify you by email if there's a problem with one of your simulations. You'll notice that all these files are being saved into the $process folder, and they're all assigned names. So your $process folder is your simulation subfolder that we just created with the script. So the folder's numbered from 0 to 24. Then there's a few commands about when to transfer output files, and then you reach your executable line here. So this tells the Condor queue where the executable is that it needs to run. So we've got our one executable called CrystalGrower.x in our folder. We're just telling the queue that that's the program that we want to run. So then you have your input. This tells the queue where it's going to pull answers from the keyboard from. So just as we fed in add input to replace keyboard inputs on our local machine, we can feed in add input to allow high throughput jobs on Condor. And we know that that file is located in each of our sub-simulation folders, so the $process file. So what that's telling the queue is, for each simulation, go into the folder and feed in that addinput.txt file as parameters to the program. Then we know there's also a few other files that we need as inputs. For example, our executable, we always need that. We need our structure file, which we've told it the location of that. We need our coloring file, which is our CHA facets found file. And we also want to transfer all the files that are inside the $process file. And that's what that line means there. So if you're using a net-based structure, this is the point where you would want to input your net.txt, because that needs to be transferred with all the files too. It can work the same way as the structure file, where you just have one net.txt in the top directory, but it can also work the same way as an add input or input.txt, where you have one per simulation folder. Then we need to tell the queue how many jobs we're going to queue. So in this case we've got 0 to 24, so we need 25. So once that's set up correctly, we know we've set up all our folders correctly, all our files are in the right place, we need to actually submit to the queue. So let's leave the submit.txt file. So the normal command for submitting to the Condor queue is Condor _submit. Then you need to provide your job submission script, which in this case is submit.txt. And then you can press enter. And you can see that that's now submitted 25 jobs to the cluster. It also gives you some tips on how to improve your submission file. If you want to check on the progress of your jobs, you can use the command Condor _queue. It'll give you a nice summary of all the jobs that you're running. It'll also give you a summary of all the other users that are using the Condor queue. But with the alias technique we used earlier, you can change the names of some of these commands. So I've changed my Condor queue to qstat, which is the syntax used on other HPC systems. But you can change it to whatever you want. So you can keep checking your jobs if you want to see the progress. You can see there's 25 of them running at the moment. If they're waiting in the queue, they'll be in the idle column, and then once they're completed, they'll be shifted to the done column. So you can see now that 9 out of 25 have completed, but 16 are still running. So if I type ls, you can now see that those completed simulations have now been written to my folder. So if I wanted to, I can now use FileZilla to download all these to my computer and start to visualize them. So I hope that's given you a good tutorial in how to use Condor to run batches of simulations. The power of Condor is that you can submit loads of simulations to the queue and they can be run simultaneously, saving you a lot of time versus running simulations sequentially on your machine. We also covered how you can use bash scripting to set up a batch of simulations quite easily, and how to edit your submission script to submit your simulations to the queue. With all this data that we're generating, our next bottleneck will be processing our simulation results. In the next video, I'll go through how to process a batch of simulation results using a high throughput methodology.